Good day, everyone. In this lecture, I'm going to discuss closed sets. As you will observe in the later part of this lecture, the concept of closed set in topological space is most likely the same as in the concept of closed set in the topology of the line and plane. That is, for a topological space X, a subset A of X is a closed set if and only if its complement, we have heard this notation, is an open set. So if you're going to get the complement of the given set, and if it is open, then we can say that the given set is closed. And also, if a set is closed, then it should be that the complement of that set is open. So let's try to consider this example. Consider this collection of subsets of X. This is our topology denoted by tau. So this topology is defined on X here. Now, in our previous discussion, the members of the collection, the members of tau, are all open sets. Now, if we try to get the complement of each member here, then it is closed. Okay, so here the complement of X is empty, the complement of empty is X, the complement of the set A is the set with elements B, C, D, E, and the rest will follow. Now, all of these are closed sets. So that is the complements of the open subsets of X. Now, I have a question. Is there a subset which is both open and closed? In other words, it is found here in the collection tau and also here. So it means that the set is both open and closed set. So as you observe here, we have the set with elements B, C, D, E. You can see it here and here. Another one, we also have X and MT. Now another question. What about neither open nor closed set? Do we have the set which is neither open nor closed set? It means we cannot find it in the collection of tau and as well as here. So, example of that set is the set with elements A and B. So you cannot find here AB, right? And also here, set with elements AB. Therefore, that set is neither open nor closed set. So let's have another example here. Let's have the discrete topological space. As you recall, when we say discrete topology, it means it is the collection of all subsets of X. Kumbaga, it is the power set of X. So as you noticed, in that set, because it contains all the collection of all subsets of X, now if we are going to get its complement, of course, the complement is still there, is in the collection of subsets of X. Kumbaga, it is in the topology D, script D. Therefore, all the sets there in the collection are all open and closed. They are both open and closed sets. So you can try an example for that to illustrate further the concept. So let's have here the complement of A is equal to A for any subset A of space X. So let's have this proposition 5.2. In proposition 5.2 here, we have in a topological space X, a subset A of X is open if and only if its complement is closed. So, how to prove this statement? In our previous definition, it states there that a subset A is closed if and only if its complement is open. So, the other way here is a subset A of X is open if and only if its complement is closed. Now, let's try to have an outline of this proof. So, for the outline of this proof, let's have two ways here because we have here if and only if. So, first, let's try to show this. It means we will assume that A is open. And then we're going to show that A complement is closed. Okay. Now, to show that this set is closed, of course, we are going to get its complement by the definition. So, it should be that the complement of this set is open so that we can say that this set is closed. Now, the complement of this set here is this one. This is the complement. This is the same as writing this one. And we have a previous statement that states that this is equal to A. Now, notice that A in our assumption is open. Therefore, this is open. So, it means that the complement of this set is open, which is this one. Therefore, we can say that the given set is closed. So, we're done in our first. Now, for the next one, the other way is we are going to assume that the complement is closed. So, we have, recall that we have A is a subset of X. So, we have here A as a subset of X. Then in our other way of proof, we are going to assume that its complement is closed here in our statement here. So we will assume this one and then we will show that A is open. So let's assume that A complement is closed. So let's have here A complement is closed, and then we are going to show that A is open. Now, to do this, we use the definition of a closed set because we know that if A complement is closed, then the complement of this is open. So let's have here the complement of the complement is equal to this one, which is equal, of course, to A is open, based from our definition of A complement being a closed set. Hence, we have shown that A is open. So, we have proved proposition 5.2. Now, let's have here theorem 5.3. Now, let us try to recall the three axioms in my previous videos or lectures. So for a topological space, we do have here 3 axioms. For first axiom, recall that X and MT are open. Here in the second axiom, the collection katong tau is closed under countable union. And then for the third axiom, the collection tau is closed under finite intersection. Now first, we are going to show that X and MT are closed sets. So to show this one, recall that X and MT are open in our first axiom in the topological space. Now if we're going to get the complement, so the complement of this is MT. So of course, since X is open, the complement is closed by using our previous result. Another one here, the complement of MT is X. So since MT is open here, the complement is closed. Now as you observed, X and MT are closed. So we're done. Now let's have the next here, the second. We will show that the intersection of any number of closed sets is closed. Now recall that the union of countable open sets is open. We have here for each G alpha, it is open. Now if you're going to get the complement of this, the complement is this, which is equal to the complement of the union is the intersection, then this one. Actually, we use here the De Morgan's law here. So this is closed. We are getting the complement of open. So the complement is closed. And as you observe, the complement, because each G alpha here is open, so each G alpha complement is closed. So here we have shown that the intersection of any closed sets is closed. So we're done showing the second. Now to show the third statement here, that is the union of any two closed sets is closed. Let's try to recall again the third axiom of a topological space. So for open sets G and H, we have the intersection of G and H is open. Now if we get the complement of this one, the complement by using the De Morgan's law, which this is equal to G complement, the intersection becomes union, then H complement. Now observe here that G complement and H complement are what? Closed sets, because G and H are open. So closed sets. Now here we have shown that the union of two closed sets is closed. So this is closed. Why? Why is this closed? Because G intersection H is open, and then by getting its complement, this is the complement is closed. So we're done showing the three conditions here. Hence, the class of closed subsets possesses the following properties. These three properties here. So, closed sets can also be characterized in terms of their limit points, as in Theorem 5.4. So, a set is closed if and only if it contains each of its accumulation points. Or in other words, we can have this one. A is closed if and only if the derived set is contained in the set itself. So that's it. In my next lecture, I'm going to discuss closure of a set.